Hello again everyone, welcome back to ptet.chemistry channel. So in this short tutorial video covering topical MCQ, this is going to be on the states of method. This is topic number 4 in the Cambridge International A-Level or whatever curriculum that you're using, okay? Or doing, really. So this is a question on gases and their pressure. So we know that from Boyle's law that you will have done in physics, I guess, in O-level physics, and you will have revisited this in A-level chemistry. The pressure of a gas is inversely proportional to the volume of a gas in such a way that PV is equal to constant. Alright, so because of that relationship, when we have a flask X and a flask Y, okay, where flask X contains one gas and flask Y contains a different gas, when you mix them together at constant temperature, so that relationship is only true at constant temperature. So you're going to have the P1V1 from the first flask. You add in the P2V2 from the second flask. When you mix the two together, they're going to give you a P total, V total. Okay. So from the first flask, you have 2 kilopascal. So there's 2 kilopascal multiplied by V1, which is 1 dm cube, plus P2, which is 1 kilopascal multiplied by 2 dm cube. So it's kilopascal dm cube there. I'm just maintaining my units. I want to find out the total pressure, which will be in kilopascal, because when I use the word equal, if this is kilopascal times dm cube, when you sum them up, it's going to be equal to kilopascal times dm cube. Okay, what is your new volume? You sum up a 1 dm cube gas and a 2 dm cube gas, you are going to get 3 dm cube gas because you sum up their volume. Okay, that's very important there. So 2 times 1 is 2, plus 1 times 2 is 2, so that is 4 is equal to P total times 3. So P total is 4 over 3, the unit will be in kilopascal. 4 over 3, if you convert it into mixed fraction, is 1 over 3, okay, instead of leaving it as an improper fraction, which you would have done in primary school. Okay, so next question, 4a part 2. This is about the chemistry of solid iodine, which is part of your case study in A-level. So what does it tell you about the iodine? So this is what you call sublimation. Sublimation is a process where the iodine solid goes to iodine gas. Okay, you need heat because you are going from solid where the molecules are tightly held together. Well, not so tight, but you know, they are close enough to each other. They are ordered in a regular lattice. You learn all this as the arrangement of solid particles, which in this case, the particle is iodine molecules. You learn all that from your O-level under the arrangement of solid, liquid, and gases. And then you heat it, you apply energy, you separate the molecules further and further apart, because as you could see, both of these, they are simple molecular. So what happens with simple molecular structure is that you do not break the covalent bond, but you simply break the weak intermolecular forces, which is just van der Waals between the I2 molecules. You don't break any other intermolecular forces simply because it's iodine bonded to itself. It is a non-polar molecule because even though they're electronegative, you're bonded to yourself, so there is no difference in your distribution of electrons in this covalent bond at all, based on the definition of electronegativity. Okay, so solid iodine is actually molecular. Vapor iodine is also molecular. I spent some time going through this idea because the molecular structure of iodine, including the structure and the bonding, not just within, which is covalent bond, but also between the molecules, they are always focused and emphasized upon in A-level chemistry. Yeah, okay. So next question is basically giving you some background information, and then they say which one is the most volatile. Okay, so volatility is to do with how easy to boil. So this is come down to your understanding of the word. So most volatile means it's the easiest to boil, okay? Volatility is to do with how easy to boil. Therefore, most volatile means lowest boiling point or smallest boiling point, okay? So these are all simple molecules. Because they are all simple molecules, they have simple molecular structure. We are talking about breaking the weak intermolecular forces, okay? So what sort of intermolecular forces we are talking about? Here, you will just have van der Waals. These are your classic hydrocarbon, compound containing carbon and hydrogen only. So there's only is a non-polar molecule. We're just looking at van der Waals. Here is something that you would do eventually in organic chemistry. It has a dipole. It has a carbon double bond oxygen. So that is polar. It makes the whole molecule polar. You have just permanent dipole. Whereas for this one, what you will have is you will have R and H and H. So you can have delta minus like that. But what happens is between a different molecule, you can have hydrogen bond between them, because now you have fulfilled the requirement for hydrogen bond. That is, hydrogen bonded to a highly electronegative element like oxygen, nitrogen, or fluorine. That's condition number 1. And you have fulfilled condition number 2 that a lot of students will have missed out, is a lone pair. So that one, nitrogen, oxygen, fluorine, 2 hydrogen, the lone pair on the electronegative element. Notice how I actually drew out the lone pair on the electronegative element, because you cannot form hydrogen bond if this lone pair is not available on the electronegative element. That's your second condition as part of the definition of a hydrogen bond. So here you can form the really strong hydrogen bond. Immediately you can tell this one is going to have the highest boiling point, but not really. I mean, that one can also form hydrogen bond, because you must have learned hydrogen bond in comparing HF versus H2O versus NH3. That is a case study of hydrogen bond in air levels, okay? So we know that HF is a gas, so this is at room temperature and pressure. H2O is your liquid water at 25 degrees Celsius, okay? NH3 is a gas at room temperature and pressure. That is your case study from Haber process since O-level already. What you used for your experiment in practical chemistry, what that is actually aqueous NH3. Aqueous NH3 is a mixture, okay? It is dissolving the gaseous NH3 in water. So it's not pure NH3, it's dissolving NH3 in water. That is called aqueous NH3. But ammonia is a gas at room temperature and pressure. You have done this as Haber process in O-level chemical equilibrium, as well as under nitrogen chemistry. Okay, so this one has the highest boiling point, because if you think about it, the nitrogen, just like in ammonia, only has one lone pair there. It only form one hydrogen bond per NH3. What water can do is that the oxygen will have 2 lone pair, just like the alcohol here. So you can actually form, you can actually form not just one, but you can actually form 2 sets of hydrogen bond per oxygen or per OH group, okay? So these 2 are actually H bond. I have to label the dipole as well. Okay, so I hope you can see that this, because of the greater extent of hydrogen bond, for the cell number of carbon, this alcohol is going to form stronger, because you can have 2 times H bond per OH compared to only 1 times H bond per NH. If I have to rank in a theory paper, you have to rank in terms of boiling point. I can say this one is the lowest, and this one is the highest, and then it followed that order exactly. because hydrogen bond in general is stronger than permanent dipole, is stronger than van der Waals. So this is the weakest to break, it has the lowest boiling point. These are the strongest to break, they have the higher boiling point. But between these two, I have just shown you what you will have learned. Okay, here is just using alcohol and amine, RNH2 and ROH. But you will have learned the exact same thing when you compare the boiling point of H2O versus NH3, which is your case study. This will come in organic chemistry as well. They love to ask it, but it's nothing more complicated than your most basic case study. I spent way too long on this, but I hope it helps to explain the idea. Yeah? So next bit is which one exists in the solid state as a giant covalent lattice. Giant covalent lattice has another name. It's called giant molecular structure. Okay, and I can tell you straight away that is your O-level case study. As a component of sand, you will have realized that SiO2 is a continuous network like that, where each silicon is bonded to 4 oxygen. Okay, so each silicon is bonded to 4 oxygen. It's tetrahedral, 109 degree. Because it's got 4 bond pair and no lone pair, because it's a group 14 element. It's got 1, 2, 3, 4 for bonding. So what happened then is this is 104.5 degree because each oxygen is bent. Each oxygen is bent in such a way that you have 2 bond pair and 2 lone pair on the oxygen. Okay, so immediately there is a factual question for giant molecular structure, which leave it interesting. Tin 4 chloride will be SnCl4, and the structure of tin 4 chloride looks just like methane, where it's 109 degree, tetrahedral, simple molecule. And obviously ice is just water, but it's a hydrogen bonded solid state structure because it's talking about the ice, and we talk about it in the chemical structure and bonding example, which you could check out in your own time as well. Okay. So in this question 5, we are back to gas laws. We talk about a pressure P and same temperature T. So that means constant temperature. Constant temperature. So 2 grams of hydrogen. 2 grams of hydrogen. So hydrogen exists as H2. But you should know hydrogen, this is the hydrogen 1 isotope, whereas deuterium is hydrogen 2 isotope. So when you have that deuterium, you have H2 like 2 like that. Okay, so the molecular mass is actually 4. Hang on. Yeah, the molecular mass will be 4. The molecular mass of H2, 1H2, meaning hydrogen 1, diatomic would be 2. Okay, so we know that PV equal to nRT. So what else is constant? What else is constant? We want to exert pressure. So it's nRT over V. So we know that R is just your molar gas constant. So it is just a constant that I can take it out of the proportion. And temperature is constant as well because you have the same temperature. So if I have the relationship, it's just N over V. Those are our variables. Here you know that you have 2 grams of that sample and you know the molecular mass, so you can work out the mole there. So for the reference sample, so P is equal to, well, P is proportional to 2 over 2 because the molecular mass of this hydrogen, which is H1 diatomic, so it's 2 at the bottom. The 2 comes from the 2 gram. Okay, so that's over the volume V. So that gives me the pressure of that is proportional to 1 over V. So all I need to do is I need to work out the relationship, the mole over the volume V, well, over the volume of the whatever species this is, taking in mind that these are deuterium and these have a mixture of hydrogen and deuterium. Okay, so if I do that very quickly for option A, So my P will be proportional. I don't use the word equal because I don't want to have to put in the R and the T. So I just use proportional. I should get 1 over V for it to be the same pressure as this original sample there. It should be 1 over V if I work out the pressure in that relationship, yeah? Okay, so what do I get? So maybe I should just be looking at N over V, which is the number of mole. So 2 gram over 4, because deuterium is the hydrogen 2. There are 2 of them because it's diatomic, so the molecular mass is 4. So it's 2 over 4 on top, and then the volume is V. So there is 1 over 2 over V. There is 1 over 2V. It is not 1 over V. So A cannot be the answer. We are looking for a relationship of mole over the volume, give us 1 over V. Alright, so moving on to the next one, part B. So you have 4 gram deuterium, so it's 4 at the bottom there. The volume is V over 2. The volume is V over 2, so that's 1 over V over 2. That means 1 times 2 over V. Your primary school mathematics, when you divide by something, you become times the reciprocal of it, okay? So 2 over V is not 1 over V. Again, B cannot be the answer. Alright, how about if we are looking at C? C is a bit tricky. You have 1 gram. So you have 1 gram of, so the N over V is going to be the 1 gram of hydrogen, so it's 1 over 2. Your total volume is V there, so it's 1 over 2. But then your number of mole is the sum of the number of mole of gas. So it's going to be 1 over 2 for the hydrogen, 2 over 4 for the deuterium. The total volume is V. You sum up the number of mole, yeah? Okay. So that one is for option C. That is going to give you, so that is a half as well. A half plus a half is 1, so it's 1 over V. Oh, there you go. So C is the correct answer there. Okay, and you could very quickly work out why D is not the correct answer. I mean, by the time you get this right, I don't really need to work out D, but I'll just show you why D is incorrect. So 2 over 2 for the hydrogen, 1 over 2 for the deuterium, divided by the volume is 2V. So 2 over 2 is 1, so there's 3 over 2 over 2V. So there is 3 over 4V. So again, D cannot be the answer. So a bit confusing here, okay? But the R and the T are constant. We are looking at the relationship, and I guess this step is the key step. Do you know that you can sum up the number of mole divided by total volume to give you the pressure? Okay, so there's volume of gases for you. So this is the end of this 5 question series for this topical MCQ involving states of matter, mostly gases really. So I'll see you in the next video. If you haven't subscribed, please subscribe to the channel, and yeah, share the words about the channel, and I appreciate it. Okay, thank you.